Do you feel like you are using trial and error for your heat exchanger design projects? If that's the case, don't worry, you're not alone. I've been there before. My first industrial heat exchanger design project was about 20 years ago. And that's the first job I actually got paid for as a consultant. But I had absolutely no workflow. I was bouncing between textbooks, Google search, but fortunately I had access to Aspen HYSYS. Look, it was a bit of a mess, I must admit, but it forced me to learn something very fundamental, which is the key difference between heat exchanger, thermal design, and sizing. And today I'm going to be breaking down that exact approach that I wish I had known back then so you don't have to learn it the hard way. It's very common to see engineers get right into the deep end of heat exchanger design, focusing on mechanical details and shell types and all other bits and pieces. But there's a problem with that approach. If you don't establish the energy balance first, the rest of the design simply won't matter. So over the next 4 videos, I'm going to show you how to navigate the full design process within Aspen HYSYS. We are going to follow a professional workflow, the same one that is used in the industry. We are kicking off things today by building the foundation. In this lesson, we are going to cover 3 things: finding the unknown flow rate, calculating the total heat duty, and of course, setting your first working simulation. This is the professional standard for any design project. While these steps are straightforward, they are critical. If the energy balance isn't accurate, you'll end up with a heat exchanger that is incorrectly sized. And we are going to make sure that doesn't happen. Before we open HYSYS, let me ask you a question. If I give you a hot stream and a cooling utility, who is the boss that decides how much heat is removed from the hot stream? Take a moment and think about it. It's not the type of heat exchanger you choose, and it is not the internal geometry. It is the conservation of energy. Every heat exchanger follows one fundamental rule. The energy lost by the hot stream must be equal to the energy gained by the cold stream, and that's the physics of the system. And this is exactly why we start here. Before you design a single piece of hardware, you have to define the energy moving through the process. Let's put this into practice. You are tasked to design a heat exchanger, and you've got a hydrocarbon stream at 180 degrees, flowing at 6,000 kilograms per hour, and you need to drop the temperature to 50 degrees Celsius. For cooling, you are using water that comes in at 25 degrees. But here's the catch. You have to stay within a specific operating window. To prevent scaling and fouling, you can't let the cooling water get too hot. So typically, we limit the outlet temperature of the cooling water to be around 45 to 50 degrees Celsius. This constraint changes everything. It's no longer just about cooling the stream. It's about a specific energy balance. The question is, how much water flow do we need to heat our target temperature without exceeding the safety limits? Okay, enough talk. Let's get into it. We are now in HYSYS, and as usual, we are going to start by adding our stream components. This time, I want you to pay close attention to the workflow because some of the steps are going to be slightly different from what you're used to. But stick with me because it will all make sense at the end of the day. And this is going to help set your model apart from anything you've ever built before. First, I'm just going to add the components. We got benzene, enter, and then second one is toluene, enter, and then I'm going to rename this components list folder to hydrocarbons. And then we're going to assign a property package to this hydrocarbon folder, and the property package is Peng Robinson. And then I'm going to rename that property package folder again to Peng Robinson. And you might ask, Alex, why are you doing this? It sounds a little bit of too many steps. The reason I'm doing this particular step is to make sure that I can be able to separate the hydrocarbon stream and the cooling utility stream, which is the water. Both streams will be using two different property packages. One is Penn Robinson for the hydrocarbons, and one is NBS steam for the water side. Remember, in the heat exchanger, these two streams don't actually mix. Hence, that's why we need to have the property packages separated. Okay? Now, we have done this bit. Let's add the water component. And we go to the component list to search for water. Add it, press enter, and then rename that folder to water. And then we're going to assign the property package to the water component, and then rename the water property package to NBS steam. And you click OK. Now that part is done. We have identified our components. We have also identified the utility stream. The next thing is to jump over to the simulation environment. I'm going to start by docking this. And then first thing that we do, as usual, is to insert our material stream. I'm going to double click on that material stream and then rename it. You'll see my workflow has a lot of renaming steps so that when you come back to the model in 6 months' time, you know what was happening, right? I'm going to rename that to hydrocarbon hot. And we know the inlet temperature of our hydrocarbon stream was 180 degrees. And then the pressure is 650. That was not explicitly mentioned in the problem statement. I will show you how that 650 is actually very important. The flow rate was 6,000 kilograms per hour. And then HYSYS tells us that we need to insert the composition. Click on composition and then go edit. And then the benzene is 44% or 0.44 mole fraction. And then the toluene is 0.56 or 56%. Then you got OK. That stream is fully specified. But before we do anything, we're going to check whether this stream is actually at boiling point or far from boiling point. Because when you do a heat exchanger design, there's two things that can happen. You can either design a heat exchanger for just a liquid phase stream or a gas phase stream or a two-phase stream or a stream which has got a phase change happening in it. And the energy balance for those components would be completely different. The first thing that we need to check is what is the phase of this stream. What I've seen is most engineers skip this step and things start to go south pretty quickly because of if the stream has a phase change and you missed it in the first setup, you're going to end up with a completely different heat exchanger. Now, let's run a stream analysis to see what's happening with this particular stream. You just click on it and then you go to stream analysis and then you go to the master phase envelope. Then you will have already clicked on the hydrocarbon hot stream. Now we're going to go to performance and then we want to see a plot, right? So click on the plot, tick this little tick box there and then go to plot. HYSYS will plot your phase envelope for that particular stream of 44% benzene and 56% toluene. So you will see that diamond shape there, which is there, that's our operating point, right? And then the red line is the boiling point, and then the blue line is the dew point. And then between these two is a two-phase region. So you will see that our stream is actually very close to boiling point. Let's just zoom in into here. I'll just click on the chart and then drag, and I'll do it again just to zoom in. And you can see at 650 kPa at 180 degrees, this stream is pretty close to boiling point, right? So what does that tell you? That tells you that it is still in liquid phase, most of it. But if you were to drop the pressure any lower, then you will be at boiling point. And then if you continue dropping the pressure, you will have a two-phase region in that exchanger. So the pressure drop in this heat exchanger is going to be very important. We need to be very careful of that. Now that we have some sort of an idea of the allowable pressure drop, or at least an indication of what our allowable pressure drop range should be, then we can go ahead and start playing around with the thermal design of the heat exchanger. Okay, I'm going to close this window here. And now for the thermal design part of the story, we are just going to first use a cooler. And I'm going to bring it into the canvas and then call it a cooler. And then the inlet stream is this one here, the hydrocarbon hot. And then the outlet stream, I'm going to just name it hydrocarbon cold. And then we also need to specify the energy stream. I'm going to call this one the cooling duty. And then you'll see HYSYS will ask you what's the pressure drop. Like I said, at this stage, we are not sizing the heat exchanger. We are not doing any physical heat exchanger design. We just try to get the thermal design out of the way. And to do that, I'm just going to say the pressure drop for now, 0. I'm not too worried about that. And then just tidy up this flow sheet here. Look at this. Remember, we said our target temperature for the hydrocarbon stream is 50 degrees. We want to cool it down from 180 to 50 degrees. Just double click on the stream here and then change the temperature to 50, and it should calculate the cooling duty. So from a thermal design perspective, I think we've done all the steps that we need to do here. Let me just resize that, and then you will see that the cooling duty is 423 kilowatts, right? So let me just put a table here. I'll just right click on the stream there and then show table. It shows us that, okay, this heat exchanger, whatever you do, it will need to have a minimum of 423 kilowatts cooling duty. So that's the first step done for the thermal design. The second step is, okay, we know that we need to remove about 423 kilowatts of energy from the stream, but how much cooling water do we need to achieve this? We don't know that yet. And the quickest way, or the smartest way to do it first, is to come here to Utility Manager, because we know our cooling utility is cooling water, right? But you'll see HYSYS has got default values of 25 for the outlet and then 20 for the inlet. Remember, in our program statement, it said the cooling water outlet for this specific region that we're designing this heat exchanger is allowed to go to 45 degrees. So I'm going to change the outlet temperature to 45 degrees. That's our maximum allowable outlet temperature from the heat exchanger. And then the inlet, it's 25 degrees. So here in Australia, we normally design our heat exchanger inlet temperatures to 25 degrees, which in most times it will be the cooling tower outlet temperature. Once you've done this, you can close this tab, you double click on the energy stream, and then we're going to specify the utility type. For the utility type, we go and on the drop down, we select cooling water, and boom, what it does, it calculates the utility flow rate. So you can see that the water flow rate that we need is about 18,210 kilograms per hour, right? So I will just double click on this table that we have here, and then I'm going to add that flow rate. Just search for mass flow. Mass flow, and then I'm going to rename this to water flow rate. And there we are. From a thermal design perspective, as a process engineer, you ask me, oh, so how big is this heat exchanger? I'm going to say the heat exchanger is a minimum of 423 kilowatts. And you're going to need about 18,210 kilograms per hour of cooling water. In that way, as a start, I am comfortable that this heat exchanger will be properly sized because of whatever mechanical design that you're going to implement. This is the minimum thermal rating that the heat exchanger needs to have. And this will be the minimum flow rate of water that you're going to need to go through that heat exchanger. I hope that makes sense for now. And if it doesn't, it's okay. We will take this one step further and then start playing with a shell and tube heat exchanger. It wouldn't be a rigorous design just yet, but we are now going to use a semi-physical unit to model the heat exchanger itself. And that will be the second video from this one. Please go and play around with this, get comfortable with the steps that we just took, and then I'll see you in the next video. Cheers for now.